Welcome back, student. To this lesson, we will talk about partially ordered set, and today we will talk about a new type of relation between element in a set A, and this relation will put an ordering on the elements of A. Ordering means it will give me a way to say that A is related to B, something to mention that who is bigger than who. So we'll say A related to B if A in some sense less than B. It will give me a relation in that way. So let me start directly with the definition. What do I mean by a partial order relation on a set? So we will start with a set A. So let A be a set. Of course, it should be an empty set. A relation R on A is said to be partial order relation if R is, it satisfies the three condition, which is reflexive, so each element is related to itself, transitive, which means if A is related to B and B related to C, then A related to C, and finally it is anti-symmetric. So we only can have A is related to B. I cannot have also at the same time B related to A, unless of course A is equal to B. But here anti-symmetric means it is only A related to B, and then you cannot have B related to A. This cannot happen, one of them. Maybe none of them happen, that's fine, but if one of them happens, the other cannot. So this is what we call it, partial order relation. And as a note or as a notation, if we have a set A and this relation, this is called partial ordered set. Sometimes we just call it POSET. That's what we have here. So now let me just do two easy examples here, just to give you the main examples that we will see mainly in this topic. So example number 1, consider the integer and my relation is the following. So my relation will be A is related to B. It means, or it happens, when A divides B. Remember, this is A divides B. Which means, in short here, if B is equal A times K for some K. If this happens, this is a partially ordered set. And why this is true? Because we need to check the three conditions. First of all, why it is reflexive? Because A always divide A. Why? Because A is equal 1 times A. This is my K here. So it is reflexive. Now, it is transitive. Yes, we proved before that if A divide B and B divide C, then A divide C, and we can also prove it very quickly here. And very easy. A divide B. This means B equal A times K. B divide C, this means C equal A times L. Now if you combine this, B times L, if you combine this one, C will be equal to AKL, which means A divide C. And of course, this is anti-symmetric. You cannot have, if A divide B, you cannot have B divide A unless they are exactly equal. So this is the first famous example of a partial ordered set is the divide relation. Example number 2, also important in terms of a subset of a set. So example number 2, I will take the relation on the power set of A. Power set of A. And here I will say that two subsets, let me call them two subsets, X related to Y, those are subsets of A. Those are related if X is a part of Y. Of course, we can see that this is reflexive because every set is subset of itself. We have seen this is transitive. If X is subset of Y, Y subset of Z, so the very small one will be subset of the very large one, and of course it's anti-symmetric. If it happened that X is subset of Y, and if it happened Y subset of X, they are exactly the same, and this is how we define it. So those are the main two examples. We have also some other examples, but those are very nice examples. Let me now go to example number 3, which can be applied to any set of numbers. And I think this is a famous one here. Example 3. In this example, I will take only a couple of numbers, 1, 2, 3, 4, and 5. And my relation will be that two numbers are related if and only if A is less than or equal to B. Which means I will take two numbers here, I will check are they related to each other if one of them is less than the other. So in this case, 2 of course will be related to 4 because 2 is less than 4. 3 will be related to itself because 3 is less than or equal to 3. But what about 5 and 1? This is no. Why? Because 5 is not less than 1. It is 2, 1 is less than 5, but not 5 less than 1. Again, this is an example of a partial ordered relation. So this is a partial ordered. Now, as we did before, usually representing the partial order is a very good thing if we can do it using graph. And this is exactly what we will call it Hasse diagram. So we have something, we call it Hasse diagram, where we can represent the relation in that way. Especially if it is finite, we can deal with it. Now, if you remember, the old way or the previous way is to write those as nodes. 1, 2, 3, 4, and 5. And then I have to put a loop for each one because it's reflexive. We know that every number is less than or equal to itself. Now we have to join the nodes. So because 1 will go to 2, 1 will go also to 3, 1 will go to 4, and 1 will go to 5. Next, we'll have 2 goes to 3, to 4, and to 5. Next, we'll have 3 goes to 4, 3 goes to 5, and finally we'll have only 4 goes to 5. This is how it looks. Of course, all the arrows are one way because it's anti-symmetric. We cannot have them both ways. And this is exactly what's happened here. Now, there is the Hasse diagram is a little bit different. And it's very much easier for us. The Hasse diagram says that, for example, I will start with 1. Because I know it is reflexive, I will not put anything. I will not put a loop. I know there is a loop, but I will not write it down. Now, look at the first step. 1 is related to whom? To 2. So I will put a 2 above 1. And I will write 1 arrow. I will not put a direction because all my arrow will go upward. I don't need to put an arrow here. Since I write 1 down, 2 above it, I know that this will go from down to top. That's how we will write it down. Okay, now we finish from 2. Now I can start doing 3. Okay, so I will put 3 here. And now, because 2 is related to 3, I can just continue my arrow. Now, do I need to go from 1 to 3? This is no need. Why? Because it's transitive. I will go from 1 to 2 and then 2 to 3. So I don't need to write the shortcut. I will just go through 1 to 2 and 2 to 3. Why this is possible? Because it's transitive and I already have 2 goes to 3. Now 3, it will go next to 4 and 4 will go next to 5. So in this example, I will get what we will call it chain, starting from the very bottom, going all the way up. This is the first example here. Okay. Now, if you look at this Hasse diagram here, you can reveal all the information. Is 2 related to 5? Yes, because I can go this way and I reach 5. Now, is 1 related to 4? Yes, you go from 1 to 4. Is 4 related to 2? No, because I can't go downward. All my arrow will just consider them going upward. So from the Hasse diagram, I can reveal many information about my partial order relation. Let's go and see another example. Now, this example will be about when we do the divides. Example 4. My set is 1, 2, 3, 4, 6, 8, 12. And my relation is the following, is the divide relation. So 2 numbers are related when one of them divides the other. And the question is, I want you to draw a Hasse diagram and find a chain. So let's see the solution. Of course, drawing a Hasse diagram should be something we can easily do. And here how we will go. So first of all, I will start with 1. So this is 1. Now, what is the relation between 1 and 2? We know that 1 divides 2. So it will go like this way to 2. Now, is 2 divides 3? The answer is no. So I cannot go and continue from 2 to 3 because this is wrong. So I cannot put 3 above 2. So I need to put 3 in the same level of 2 because I can't go above it. So I will write 3 here. And that's good. That's a good one here. So now it's clear. I take care of the first 3. 1 divides 2. 1 divides 3. And I cannot put 3 on top of 2 because 2 doesn't divide 3. Now, how about 4? Well, I cannot put 4 on top of 3 because 3 does not divide 4. So I will put 4 on top of 2 because 2, of course, divide 4. So I get 1 divide 2, 2 divide 4. So here I will go. I will add 4. Okay, next what we have here. Next is 6. Of course, I can't put 6 on top of 4 because 4 does not divide 6. So I will need to put it in the same level. Put 6 here. Now let's see. Is 3 divide 6? The answer is yes. So I will put an arrow. Now, is 2 divide 6? The answer is yes. So I will put an arrow. Now, of course, as we said, 4 does not divide 6, so I will not put an arrow here. And of course, 1 will automatically be able to reach 6 and anywhere else because of how the chain works here. So we take care of 1, 2, 3, 4, and 6. How about 8? Well, I know that I cannot put 8 on top of 6 because 6 does not divide 8, but I know that 8 will be on top of 4 because 4 divide 8. So this is 8. And of course, I cannot put this arrow here. No, because 6 does not divide 8. And of course, I don't need to write from 2 to 8 because I have a 2 to 4, 4 to 8. So I'm trying to minimize my arrows. And I think finally is 12, and I'm sure that 12 will be in the same level of 8 because 8 does not divide 12. Now, let's try. How about 6? Is 6 related to 12? Does 6 divide 12? The answer is yes. So 6 divides 12. Now, where else? Of course, 3, 2 goes to 12, 3 goes to 12. How about 4? Does 4 divide 12? The answer is yes, because 12 is 3 times 4. It's multiple of 4. We get this one. And I think finally, 8 will not divide 12. So this is the final answer here. So looking at the Hasse diagram is very nice because now I know who is related to who in terms of divides. I know that 2 related to 12, 2 related to 6. I know that 3 related to 6 and 12. And you can see that even 4 can go to 12. And that's how we draw the Hasse diagram. Next is to find a chain. Remember, a chain is something looks like from the very bottom to the very top. And it should be one line going from the bottom to the top. So here we find many chain, but if you want only one chain, you can just choose this one. So chain, I will start from the very bottom, reaching to the very top. So I will go 1, 2, 3, 3, 6, 6, 12. Very top to the very bottom in a straight line. So as a chain, it will go 1, 3, 6, 12. And if you want to write it as a set, you just have to list the elements. 1, 3, 6, 12. This is what we call it a Hasse diagram, and this is the first example of doing the Hasse diagram here. Okay, the next example will be about example number 4. Example number 5 will be about the subset relation. Example 5. Here we have A to be the set 1, 2, 3, and define a relation on the power set of A. As follows. Two sets x related to y. And do we have it? We have it in this case. If x is less than, or is subset of y. And the same question as before, I want you to draw a hazard diagram. We'll do the solution. Well, maybe for this example, we need to list the power set of A. And then we start doing the hazard diagram. So if you remember how we list the power set of A, we have the empty set, we have the singletons, the one that have only one element, we have the one that has two elements, and we have the full set. Okay, now let's do it as a hazard diagram. So first of all, as sure as I could start with the empty set. Now, can you tell me what is the relation between the empty set and the set has only one element, which is 1? Of course, it will be in a different level. It will be above it. And we already proved that the empty set is a subset of any set. So empty set must goes to the 1. Now, can I put the set that contain 2 in top of 1? Can I do this? The answer is no, because 1 is not subset of the set that contains 2. Remember, something subset of something else if everything here is already repeated up there. So the 2 will be in a different level, which is this one. And similarly for 3. So we finish from the first level. Now, how about 1, 2? 1, 2, of course, it will be somewhere here. And the 1 is there and the 2 is there. Of course, I cannot add 3 because I cannot see the number 3 in this set. Similarly, 2, 3 is here, 2, and 3. And maybe finally, we can squeeze, I don't know, maybe here, 1, 3, which is 3. Something like going from 1 to 3. And in the top of everything is 1, 2, and 3. And this will be going this way, and this way. So here is like a hierarchy, like a levels. We go from one level to next one, to next one, to next one. We cannot go from level 1 to level 3 by a direct way. We have to go from level 1 to level 2, and from level 2 we can reach level 3. And this is how it looks like in this example. Okay, now I would advise you to pause this video now. Try to rethink about everything we did, the hazard diagram, because now we will start revealing some definitions, some names for things in the hazard diagram. So what I will do, I think this is a very good example to me. I will copy this example and we will write the definition, keeping this example with us. Keep it for now. Now, what we will do next is definitions. And there are so many of them. But with the help of the example, they will be Now, do you remember when we did equivalence relation? Usually we said we would denote it by tilde. For partial ordered sets, if we have a partial ordered set in general, I will not call it R. For partial order relation, we will use the notation. Look at this notation, I will write it in this color. It is like less than or equal, but I will put it in a curly way instead of R. So this is actually a notation, not a definition. So that's what we will do. It is not similar to less than or equal. Sometimes if you want just to emphasize it, I will write it like this. It will give me an idea that they are kind of less than in a way, but not exactly less than, because maybe we are not talking about numbers as the usual way of writing as a number. Now, what is the first definition we have? Definition. Well, the definition says that two elements, A and B, if they are related, A and B are related. Of course, what do we mean by are related? It means A has a relation with B. We write it that way. This is, we will call them A and B are comparable. It means I can't compare them. I can't say one of them kind of having higher level than the other. So we call them comparable. Now, what happened if they are not? We will call them A and B are not comparable. I cannot compare them. They might in the same level, maybe they are in different level, but there is nothing between them. They are not related to each other. Well, let's look quickly at this example here. For example, 3 and 12 are comparable. Why? Because I can go from 3 to 12, from this level to this level. There is a way. 2 and 12 are comparable because I can go from here to here, or I can go from here to here. There is a way to move from one to other. How about 4 and 6? They are not comparable. You cannot go from 4 to 6 or 6 to 4. There is no way you can do it. Remember, you can go up, but you can't go down. Similarly, 8 and 12, are they comparable? No, because they are not on the same level. Even 3, which is very down here, is not comparable to 8. You cannot go from 3 to 8. So in this case, 3 and 8 are not comparable. So comparable means in the Hasse diagram, there is a way to move from one level to the other one in a different level. For example, 1 is comparable to everything. From 1, you can go to anywhere you want. So it is comparable to everyone. This is the first definition here. Second definition. As I said, we will have now a couple of definitions. We just need to keep them in mind. Now, a POSET A POSET means a relation, and I have a partial order, something like less than or equal, such that every two elements are comparable is called totally ordered relation. Totally ordered. Sometimes we call it linear order, and sometimes we just call it a chain, single chain. Now, what does it mean every two elements are comparable? It means if we do the Hasse diagram, any two elements will just go with each other. And that's what will happen here. So it's a kind of a chain. Chain means from one element I can go to the other one. Now, if all of them are comparable, they all must be in the same line, going like a line. This is why we call it a linear order. Okay. Next definition. Next definition, I want to give those some names. Those. We will call them maximal or top. This is top. Why top? Because there is nothing above it. Why this is top? Because this is nothing above it. So it is the top one. And this one, because there is nothing below it, we will call it minimal or bottom. So we have two definitions, maximal and minimal. So definition. The first one we call A as maximal. Sometimes we just call it top. If there is no B such that A goes to B. There is no B above A. A is the top manager. Sometimes if you have a company, you have employees, you have a top manager who is the highest one, no one above him. This is we call him top. And in some companies, there are only one, and some other companies, there are many top manager, for example, focusing on different part of the business. So sometimes you have many top management together. And then there is the minimal, which is the bottom. If there is no B such that B is less than A. Now with the Hasse diagram, it's easy to understand those definitions because we just need to look at the Hasse diagram and see the maximal, the one that has nothing above them, so it is 8 and 12. The minimal or the bottom is only 1. Now 2 is not a maximal because there is something above it. It is not minimal because it is something below it. So we are just focusing on the higher level and the lowest level. Let's see. For example, in this is a maximal because nothing above it. And this is a minimal because there is nothing below it. So it's top and bottom. If we look at this chain, this is the maximal or top, and this is the bottom. Top and bottom. So this is the definition. Of course, I will write the definition and we will discuss them now in one big example to see the meaning of each one. Last definition is a little bit, sometimes maybe it could be confusing, but let's see the difference. Now, A, sometimes we call it largest. What does it mean, largest? Okay, largest means it should be something like a top. No, largest means it is the only top. It's only one top. We call it largest. Sometimes we have many tops, so none of them is the largest. When I say the largest is only one top, which means if we write it as a math equation, it means everyone is less than B, is below B for all B. If everyone is below B, it means everyone reports back to A, everyone is under A, so this A will be the only one who's in the top, and he's the only top, so we call him largest. And then we have A, we call it smallest or least. Sorry, it's not, let me just use the word greatest better than largest. Greatest. And then we have the least. The least means if A is below everybody. That's what we call it least. Let's go and see our example if we have a greatest or least. If we look at this example, we can see that 1 is the only bottom. He's under everyone. So this one, we will call him least. Now, is 8 greatest? Well, because it is top, but then there is another top. So this is no, it's not greatest. The greatest means it should be something only one at the very top, and everybody has to go to that top. Similar to this example. This is the greatest, because everybody will be under it, and it's in the only top. And this is the least because everybody is below it, so this is the only one here. Okay, now let me do final example and try to write what is the maximal, minimal, greatest, least, and all of these. So this would be example 5. This would be example 6. And let me just, maybe I'll just do the set A, which has 1, 2, 3, 4, 6, 12, 21, 24, 27. And the partial order relation as divides. Of course, the first question, draw a Hasse diagram. And find the largest, smallest, largest or greatest, least, maximal, which is top, minimal, which is bottom, greatest, and least. Let's do the solution. Now, please, if you didn't understand so many of this video, this example will explain everything. So let's do it step by step and exactly the same. As I mentioned before, doing the Hasse diagram is the most important part. So I will start with 1, and then I will look at 2. Where should I put 2? I have to check, is 1 divide 2? It means, is 2 multiple of 1? Yes, it is. So I will put it somewhere here. Now I finish from 1, 2. How about 3? Well, I cannot put 3 on top of 2 because 2 does not divide 3. So I have to open a new branch. I keep it in the same level. I'll call it 3. Now, how about 4? Well, 4 will be, of course, on top of 2. So we just add 1. This is 4. Now, 6 can be on top of 3, but also 2 will go to 6. Because remember, it has many ways to go there. I think 12 next will be on top of 6. And I believe also 4 will go to 12. The next one is 21. Well, 21, where should I put it? It should be above 3. But it cannot be above 2, it cannot be above 6, it cannot be above 4, it cannot be above all of these. So I have to open a new branch here for 21. Okay, next 24. I think 24 should be here. That'd be nice to put it here. Of course, 4 has to report to 24 as well. And finally, we have 27. But 27 only related to 3. Only 3 divided 27. So I have to open another branch here. And now we finish from the Hasse diagram. Now, what is the maximal? Well, maximal are the top ones that are, they don't have anything above them, which is 24, 21, 27. We have 3 tops. If we have 3 tops, it means we don't have any greatest. Greatest means we need only 1 top, 1 at the very top that everybody is reported to it. How about minimal? Minimal, I think it's only 1 that has nothing below it. And because we have only 1, it will be also the least. So this is the example number 6. Okay. Now I will do the same example. But before I do the same example, I have one more definition. And this is a very important definition, very important thing. We will see it later, but we need to discuss it here as well. We'll call it upper and lower bounds. Well, in this example, we have lower and upper bound. So again, I will start with a POSET. Be a POSET. So I know the Hasse diagram, I can deal with it. I will take subset of A, I will call it X. And here we will say an element A is an upper bound for X if what? If A is greater than everything in X. So if you do the Hasse diagram, A should be above everything in X. And should also be comparable to everybody in X. So it should be at the top of X. And similarly, an element A is a lower bound if it is less than everything in X. Okay, let's see this in an example. I think if we do it as an example, that will be very nice here. So my example will be from the previous one. Example 7. Let me just take the Hasse diagram here. Okay, now if we do this one, I will give you my X to be 2 and 6. And I will ask you find upper bound and lower bound. Well, if you want to find upper bound and lower bound, first let me just color my X, 2 and 6. Now I want you to look at this picture and give me all the numbers are that on top of 2 and top of 6, on top of both of them. So will be, I think for upper bound is easy. I can see them. Well, I can see 12 is in both of the 2 and 6. 2 and 6 can go to 12. I can see also 24 in both of them. And I think in this case, also I can see that 6 is with them. Look at 6. 6 in the top of 6. 6 is in the top of 2. So sometimes someone from the set itself. And let's see, look at the lower bound. Who is below 2 and 6? Well, I can see the 1 and I can see the 2. Nothing else. Now, why I can't say 3? Because the 3 is not in the below 2. It should be either below 2 or it's 2 itself. But 3 is in the same level. So you cannot take 3 with you in this example. Finally, I want to mention something very important here. Look at this one and look at this one. Keep them in your mind. We'll go now to another example where we need to see something here. Example 8. Last example. In example 8, I will give you the POSET. So the POSET start with A, go to B, B go to D, D go to G, G go to H, and from the other direction, C, E, F, I. And then B go to E, B go to F. Well, first of all, what is the top? What is the maximal? Well, the maximal are the one in the very top, so H and I. What is the bottom or the minimal is E. Do we have a greatest? Greatest means the top of the tops, the only top. No, because we have two tops. Do we have least? Yes, which is E. So far, so good. Now, I will give you this set here, and I want you to find for me upper bound and lower bound. Now, what is the set? The set X is A, B, C. So what is A, B, C? A, B, C. Who is in the top of A and B and C? Well, I can see that E is there. Look, E is in top of C. E is in top of B. And of course, I can go from A to E, so E is in top of A. Can I choose D? The answer is no. Why? Because D cannot be on top of C. I cannot go from C to D. It should be whatever I write here is for sure comparable to all of them. Who's next? I think next is redundant, will be F, and maybe H, and maybe I. So everything in the top of E. Now, as I just mentioned before, this E is a special one. Why it's a special one? Because it is the least one. It is the direct top, direct above all of them. See, this is the direct one. Those are just because they are on the top of E. Now, E is the very top, very direct one. So this has a name. We will call it the supremum, or the least upper bound. How about a lower bound? Well, lower bound is only E. And this is, we will call it infimum. This is the least here. Now, how about I and H? Well, I and H, there is nothing above both of them. So the answer definitely here will be none. How about the lower bound? Well, who is below I and below H, and you can have a line between them? Well, of course, there is F, and there is D, and there is E, and there is C, there is B, there is A, all of them. Of course, G cannot go to I, so I don't include it. But look, who's the direct one below them? The direct one is F. So this one has a special name. I'll just write definition for them. And this definition we say an element A is called the least upper bound if the following happens. First condition, A is an upper bound of X. Second condition, for any other upper bound of X, for any other bound B of X, A must be less than B. This means B is above A, means A is the direct one, is the only one. Thank you for watching this video. If you have any question, please write it down in the